Hello, this is Mrs. Nearing, and in this video we are going to talk through some electrolysis. So these are electrolytic cells, and what makes an electrolytic cell different from a galvanic cell, otherwise known as a voltaic cell, is that they are non-spontaneous. So some things you will notice. Let's see, get my pen to work. Okay, so we're looking at electrolytic cells. They are going to be, non-spontaneous. They're non-thermodynamically favorable, which means they're going to have positive delta G signs. And because delta G equals negative NFE, that means they have negative cell potentials. So that is something to keep in mind when we are calculating our cell potential. If we end up with a positive cell potential, but we know it's an electrolytic cell, we must have done something wrong. Okay. Um, but otherwise, things are very similar between voltaic cells and electrolytic cells in that you have a reduction and an oxidation. And since an-ox, we know that the oxidation is happening at the anode and red cat, so the reduction is happening at the cathode. And we're going to still use the same rules in that the thing that is best at being reduced is going to be reduced. The thing that is worst at being reduced is going to flip around and be oxidized. And where it gets a little bit trickier, though, with these electrolytic cells is we will often have electrodes that are inert electrodes. So like in this example, it shows carbon and steel, or it might be platinum. Um, so what that means is like if you, well, so just keep that in mind, and then we'll come back to that later, the significance of that. Okay, so let's look at this first scenario. We've got a current applied to a nickel 2 bromide solution, and that's another hint that you've got electrolytic cells. If they say a current is applied, that means you're applying electricity to this. And if you see a diagram, you'll notice in the electrolytic cells that the two electrodes are often in the same solution, and that's because since the reaction is non-spontaneous, you don't have to worry about it happening just on its own. It will only happen if you hook up a power supply. Okay, so we have to consider what is in this electrolytic cell here. So it tells us that it is a solution of nickel bromide. So I have an aqueous nickel bromide solution. So what is in our electrolytic cell then is water. Since aqueous, we know there's water around. We know there are nickel ions, and we know there are bromide ions. So these are the aqueous versions of them. Notice how there is not a solid nickel electrode. So we don't have any solid nickel. Okay, let's make a note of that. There's no solid nickel. There's also no liquid bromine present in the cell. Okay, so let's first look at our reduction. So who is going to be reduced? My things that could possibly be reduced are, it could be water, it could be nickel, or it could be bromide. Okay, so let's look at here. This gives us the reduction of nickel. Looks like this. It's got a reduction potential of negative 0.25. Then I look through and see, okay, look, here's the reduction of water. So water can also be reduced. And it's got a reduction potential of negative 0.83. And then bromine, can bromine be reduced? Well, it looks like liquid bromine can be reduced, but I do not have a reaction that shows bromine being reduced. Bromine being reduced would have to look like this. The bromine would have to gain electrons and become even more negative than it already is, which it is not likely to do. So bromine can't be reduced, so it's either going to be water or nickel. And with these two options, it looks like my nickel ion has the more positive voltage. This is the more favorable of the two reactions. So my nickel ions are going to be reduced. Now, how about oxidation? And for this one, I sometimes find it helpful to flip these reactions around and consider all my reductions flipped around and consider the possible oxidations that it could occur. So let's do that real quick. So let's flip that first reaction around. If I do that, that would show solid nickel being oxidized. This second one would show bromide ions being oxidized. The third one would show liquid water being oxidized. And then my last one would show, I guess, hydrogen gas being oxidized. Okay, so this would be my reaction down here. So let's first go through and eliminate things that do not exist in our cell. So for example, this first one, solid nickel, that reaction can't occur because we don't have any solid nickel in our cell. All we have is nickel ions. Okay, so there's no solid nickel to react. Down here in the bottom, this one shows hydrogen gas is my reactant. I don't have any hydrogen gas. Okay, so I'm left with just bromide ions and water. And if we look at, let's flip the signs around. This would be negative 1.07. This would be negative 1.23. So I could look at it as these would be what we call the oxidation potentials. So I flip them around. So the reaction that is more favorable is the one that's going to occur. So it looks like this reaction is more favorable because it's got a larger voltage. The other way you can look at it is of these two, my bromine, this one's the worst reduction. So the one that is the worst reduction is going to be the better oxidation. So that's why my bromide ions are going to be the ones being oxidized. So really the key thing about this is the fact that since the electrodes are inert electrodes, they're made of something other than nickel, solid nickel or liquid bromine, then we eliminate some of these reactions as possibilities. Like there is no solid nickel to be oxidized, there is no liquid bromine present to be reduced. So that's the big difference between an electrolytic cell and a voltaic cell. So let's scroll down and look at another example here with this one. So we've got a solution of manganese iodide. So it's aqueous manganese iodide. So I'm going to look at what's present in my container. It would be, I've got liquid water, I have manganese ions, and I have iodide ions. Notice what I do not have is solid manganese or, solid iodine. Okay. And that's important because in voltaic cells that we're used to, typically we have both the solid form and the aqueous form. But in this electrolytic cell, we've got these, inert electrodes. So we do not have any of the solid form of those ions present in the cell. So that's key. All right. So you want to look at your reduction. Okay. So if we're thinking about what can be reduced, I can either reduce water. Okay, and that looks like this reaction right here is the reduction of water. That has a voltage of, I'm not going to write the whole thing out, negative 0.83. I also could reduce my manganese ion. That's this one right here. That would be negative 1.18. Or I could maybe reduce iodine. Well, in order to reduce iodine, it'd have to become more negative, and that doesn't look like a possibility. There's no reductions of iodine ions. We've got reduction of solid iodine, but remember, there's no solid iodine in our cell. So this reaction can't happen. So really just looking at these two possible reactions. We should also point out this reaction also cannot happen because if you look at what these reactions are, the top reaction shows the reduction of solid iodine, which does not exist. And the second one is the reduction of oxygen gas, which also does not exist in our cell. So the only two things that can be reduced in our cell are water or manganese. Of these two, it looks like water is the one that's best at being reduced. So this right here is going to be my, reduction reaction. Okay. If I look at my possible oxidations, again, looking at my oxidations, I would either have to have as a reactant water or manganese or iodine. Okay, the one with, and to find my oxidations, I'm going to take my reductions and flip them around. So if I look at this reaction right here and flip it around, I will get the oxidation of water. And if I flip that around, it's going to have a voltage of negative 1.23. Oxidation of manganese, if we think this through, manganese would then turn into something even more positive, like +3, and that doesn't happen. Okay, so we don't have a reaction like that. We do have this reaction right here, which might be tempting because it has a really low voltage, which means it'd be a really good oxidation if you flipped it around. But if we were to flip it around, the reaction would be this. It would be the oxidation of solid manganese. And do we have any solid manganese in our cell? Nope. So this reaction can't happen. Iodine, though, if I took this top reaction and flipped it around, two iodines release two electrons and make I2. If you were to flip that voltage around, you get negative 0.53. So basically what I'm doing, I'm looking at these top two reactions and flipping around. This top reaction shows the oxidation of iodine. This reaction, if you flip it around, shows the oxidation of water. The oxidation of manganese ions is not a possibility. Notice how there's no manganese ions anywhere over here. So I'm just comparing these two reactions. And the reaction that is a better oxidation is this one right here. So the way we can think of it is, of these two possibilities, the iodine one is the worst reduction. So if you flip it around, it will be the best oxidation. So we should follow through the end here and actually write out this reaction. Okay, so if you're writing out your reaction, you've got your reduction looks like this. So it looks like water is being reduced, and it is forming hydrogen gas and hydroxide. My iodide ions are being oxidized, and I've got 2 electrons gained, 2 lost. Cool. If I add up my voltages, I wind up with negative, what, 1.33, and I just add these up, and you should notice that my voltage is negative. Hooray. And some cues that I have a negative voltage would be one, that they use the term electrolytic cell in the title of this homework. If they say a power source is applied, that's another kind of hint that it's electrolytic cell. And those are clues that it is, not thermodynamically favorable. And that means it has a positive delta G and a negative cell potential. So I could find the delta G for this reaction by using this equation, same as I would in a voltaic cell. My N would be the number of moles of electrons, which in this case is 2. F is Faraday's constant. It's a Coulomb per mole electron. Find that on your equation sheets. And then E is going to be my voltage, which, remember, a volt is a joule per Coulomb. So you plug that all in, you should get a delta G value that is positive, which again makes sense because this is a non-spontaneous, not favorable reaction. All right, hope that helps. Let me know if you have questions.